Hi everybody, this is Mr. Srikanth Palan here, ready to talk you through completing the square, which should get you ready for the next part of the booklet. Now, I'm going to do this set of slides a bit differently to how I've done the first few. I'm going to do a little bit more teaching, and to start with, I'm going to give you a little starter, and what I would ask you to do on the next page is to pause the video and have a go at the two starters. You probably don't need to write down very much. You might not need to write down anything at all, but have a go at the two starters, and then once you're done with that, unpause the video and I'll go through them. Okay, so hopefully you've had a look at these two questions. So what is the length of one edge of the square, and calculate the value of x. And so if you've got an area of 49 square centimetres and you're told in the question that the shape is a square, then you know that the lengths are equal, and you know that the length multiplied by itself is going to give you the area. So in this case, the length must be 7 centimetres. Okay, so that's part one done. And then calculate the value of x. Well, you're told that x add 2 is the side length, and you also know from part one that that is 7, so x must be 5, and you were told it was centimetres squared, so this is in centimetres. So that is the first starter done. Now there's a separate question, only slightly, that I'll move on to, and again I'd like you to pause the video once you see the question, have a think about it for yourself, and then unpause. So here's the additional question. What's the difference between the starter that I gave you and solve x add 2 squared equals 49? Pause the video, have a think about what might be different about those two questions, and then I will talk through it. Okay, so hopefully you've had a chance to think about why x add 2 squared equals 49 is not quite the same as calculate the value of x in the shape starter that I gave you, where I gave you an area of 49. And the main reason for that, I'll go through it by solving this equation, and then hopefully you'll see the difference. So from this line that we've currently got, x add 2 squared equals 49, I think the most obvious step here would be to square root both sides, which will give me x add 2 on the left and positive or negative 7 on the right. And there's the difference, because on part one of the starter you would have only got positive 7, because lengths of squares can't be negative. And then if I carry this on, x is therefore, so I'm taking away 2 from both sides, I should say, subtract 2, x is going to be negative 2, add or subtract 7, which means x is negative 2 add 7, which is 5, or negative 2 subtract 7, which is negative 9. So here you're going to get two answers, because this is a purely algebraic question, no context to it, nothing to say that x can't be negative. So in this question you would have two answers, 5 or negative 9, in the starter, because it was a shape question which related to lengths and areas. You know that a length can't be negative, so the length of the square had to be 7 only and not negative 7, which meant x had to be 5, positive 5 only. Okay, moving along then to completing the square. Here I've got an image of a square, and I'm going to tell you that the area of that square is x squared, which means that you therefore know that the length of one edge is x. Now, completing the square is used when you don't have a perfect square. So here you've got the same square, but you've got this rectangle added on, and we want to consider the total area of the compound shape. So I'm going to suggest that this area is bx, which means that this length is b. And in completing the square, we usually have something like that, which we're going to express in a slightly different way. We're going to express it as something squared and then subtract a bit. And the question is, why are we doing that, and how does it relate to the name completing the square? So I will show you that on the next few pages. So we had this. We know that this is x, and this is x. And a minute ago, this whole length was labelled as b, but I'm going to label that slightly differently. So I'm just going to rub that out, and I'm going to label this as half b, or b over 2, and this is exactly the same because I've halved it using the line in the middle there, which means that this area is bx over 2 and this area is also bx over 2, so that if I add those together I get the bx area that I had previously. Okay, now you're probably sat there wondering why would he do that, and I'll explain that over the course of the next few slides. So here you'll remember from what we had just now that this was bx over 2, bx over 2 here, this is b over 2, this is b over 2, this is x squared, this is x, and this is x. Hopefully I haven't lost you so far. The only thing I've changed here actually is just made the final part purple, just for this slide, because I'm going to move this section, which I'll highlight in blue. I'm going to move this section in a moment to a different place on the page. And the reason I'm doing that is because what I want when I'm looking at an area, excuse me, like this, is to be able to express it in a form which is something squared, which was like the starter was a minute ago. And what we actually had earlier on was something squared equals 49, because I gave you the area. And that's part of the reason we do this completing the square strategy, is so that we can work out lengths. That's really how completing the square originated. Now, I'll do this on the next page. I'll show you where I'm going to move that to, how I'm going to move it, and why I'm going to move it. So here it is again. But this time I have rotated it and moved it to the bottom of the original black square. So we've got our x squared here, we've got our bx over 2 and our bx over 2. So the black and purple areas are the same as what we had on the first slide that had the extended square. And hopefully you're okay with the fact that this is still x and this is still x, which means that for the purple areas, because we've got over here bx divided by 2, if this length is x, which we can see over on the left hand side, then this length must be b over 2, which we knew already. And similarly, if we know that this length is x, which we can see at the top of the page, then this length here must be b over 2. Again, we knew that already, which means, and this is important, that this length and this length are equal, and both of those have length x add b over 2. And why that's really important is because I can work out the area of this shape if I add this red dotted line in. I can work out the area of that shape, which is a square, by multiplying x add b over 2 by itself. And that gives me the area of a square. How do I know that that would give me the area of this shape? Well, because this is definitely a square. How do I know it's a square? Because the lengths I've just shown you are equal. And the only problem with that is that it wouldn't quite be the area that we want to work with. We wanted to work with just the black and the purple. We don't want this extra bit that I'll shade in green. And so we would need to take that off in order to maintain an area that was equal to the one that we started with. Okay, and that really is the premise of completing the square. The green section is where we complete it. We have something that's almost a square, which has this area, but in order to get that area completely, we have to add this extra section. And so we've completed the square by adding it on. So to get back to what we wanted, we need to get off. So what do we have here? Well, it's really important to realise that we know the area of this green square, because this length is b over 2. And this length is also b over 2. So this area, which I'll put in green, is b squared over 4. and that's because it's b over 2 multiplied by b over 2. Again, it's a square because both lengths are the same, and everything that we've been dealing with so far has been right angles, so it must be a square. Okay, and then the other areas we already knew. This was b squared, no, not b squared, apologies, bx over 2. This is bx over 2, and this is x squared, this is x, and don't forget we also know that this is x add b over 2, and this is x add b over 2. So what we wanted was the black and purple areas. We don't want the green area included, but one way we could express that is to work out the area of the red square on this page and subtract the green area, or we could add the black and the purple areas together. Okay, and those are going to be the same thing. So if I put together everything that we know now, we've got x squared, bx over 2, bx over 2, and b squared over 4. We've got x, b over 2, b over 2, and then over here, I'll do it in red to match up with the big red square. X add b over 2. And what we just said is that if we're only interested in the black and the purple squares areas together, there are two ways we can get that. We can say that the black add purple areas are x squared add bx over 2 add bx over 2, which of course is x squared add bx. But we can also say that this is the same as the red area. So this is the same as the red area, which is x add b over 2 multiplied by itself, subtract the green area, which is b squared over 4. And that's basically the premise of completing the square. You'll see how in just a moment, but the point is that we will always be replacing something that looks like that by something that is written in red on the right hand side instead. Okay, and the easiest way for me to talk you through that is to do some examples. I'll just talk you through the key points first. So you'll be able to see this in your booklet, but the completing square key points are the two that are mentioned there. Completing square for quadratic rearranges ax squared add bx add c into the form p brackets x add q squared add r. And if a is not 1, then first of all, turn it into something where you have got a coefficient of 1 by factorising out a as a common factor. It may not look like a common factor, but you're going to do it anyway. I'll give you a quick example of that just so that you understand what I'm saying. If you had something like 3x squared add 7x add 11, you can see here that a is not 1. There's your a. It's not 1. So we're being told to use a as a common factor, and 3 is clearly not a common factor of all of those terms, but regardless, I'm going to use it anyway, and I'm going to say that this is the same as 3 brackets x squared add 7x over 3 add 11. And then this part is something that we can express in completed square form, and then as a result we'll have expressed the whole thing in completed square form, and I'll show you that in an example just in a moment. So first of all, example 1, we can see here that if you think back to my diagrams, and you won't need to think back to my diagrams when you do your own questions, I'm just going to include them so that it helps you to understand what's going on. We've got an area of x squared add 6x. And the way that completing the square works is, instead of having this area over here, like that, we're going to halve it, and we're going to stick some of it underneath the original square, the x squared. Okay, so instead of having 6x over here, I'm going to take this off. And I'm going to halve it. so that I'll only be left with 3x, which means this must be 3 and this must be x. I'm going to take this off. And I'm going to pop it here instead. So we had a bit that was length 3 multiplied by x. So this is also 3x. Okay, and that is this bit here. X squared add 6x. And the point is that this area that's all in blue is the same as the area that I'm now drawing in red. Subtract the area that I'm drawing in green. And the area I'm drawing in green, well, you can see the length is 3 and 3, there and there, 3 and 3. So that area is 9. And you can also see that the red square has a length of x add 3. So the area of the whole red square is x add 3 all squared. So this first bit, the blue area, is really the same as x add 3 all squared, subtract 9. Now, it might be worth pausing the video for a moment and just double checking that you understand why this blue highlighted part is the same as the blue highlighted area that I'm just highlighting now. And why that area is exactly the same as the red square area, which is here. Subtract the green area, which is here. And so if they're the same areas, then they must be algebraically equivalent. And then, so pause the video now if you want to. I'll carry on. You can see that the question had a subtract 2, so we also need to subtract 2. And so to put it into completed square form, the final step for me is to simplify the last part. -9 subtract 2 is -11. So to write it in completed square form, x add 3 all squared, subtract 11. Okay, and now this is a much more complicated example in which we'll need to use that key point from earlier on about factorising the a when a is not equal to 1. But hopefully you're okay with that now. So I'm going to crack on and do it. So you can see here that a is 2. So looking at these first two terms, I need to use a factor of 2, which means, and if you need to do this in the grid method, that's absolutely fine. I'm thinking, what do I multiply 2 by to get 2x squared? And that's just x squared. And then the second part's a bit more complicated. What do I multiply 2 by to get negative 5x? Well, I need to multiply it by negative 5 halves x. And then add 1 because that's there at the start. Okay, now the next step is to use completing the square on just this section that I've written in blue. Now this time I'm not going to draw you a diagram, but there's two things. First of all, when it's subtract, the diagram is a lot more complicated, and really you might need to think about how it looks visually in your head. You'd need to subtract a bit of the original square, which means you'd be coming back in, and then because you've got to add that bit to the bottom, you end up subtracting the same bit twice, and so you have to add it back on. Okay, now that's conceptually quite difficult and certainly very difficult to draw, so I'm not going to try and draw it. I'm going to do the same steps though as you would do in example 1. So first of all, we need x add, or subtract in this case, something. So here we're going to use not 5 halves but 5 quarters, because we halve that section and stick it in a different place, which means 5 quarters, which is half of 5 halves. And that's going to all be squared. And if we do that, we end up with a 25 quarters that we don't want. So we need to subtract that 25 quarters. And all of that, if you look at the line above, is the same as the blue section. So in order to match up with the red line, this all needs to be multiplied by 2, and then we need to add 1 at the end. Okay, and then this needs expanding, which means we need to use the grid method. So we've got 2 multiplied by x subtract 5/4 squared, subtract 25/4, and then add 1 at the end. Now this first bit is just 2 brackets x take 5/4 squared, and the second bit, if I double 25/4, if I double quarters I get halves, so that's the easiest way to do that. And then I need to add 1, so this is equal to this is equal to this is equal to 2 brackets x take 5/4 all squared, subtract 25 halves, add 1. 1 is the same as 2 halves. If I write it like that, then I can use a common denominator for my adding fractions at the end. So I've got negative 25 halves, add 2 halves. That's the same as negative 23 halves. And that's me done. I've put it into the form that they asked for at the top of the page. So they asked for it in this form here. And I have done that. And in my answer, P is 2, Q is negative 5/4, and R is negative 23 halves. Okay, so hopefully now you can complete the completing the square section on the booklet. Best of luck. Any problems, feel free to message me on Firefly or send me an email.